Hello and welcome to this tutorial on simple linear regression by Analytics School Online. I'm super excited to share this video with all of you and get started with regression analysis. We have a lot to cover, so let's get started quickly. I've tried to give you all a deeper insight into this topic as it is one of the most fundamental building blocks to some of the most complex algorithms in machine learning, neural networks and many such others. So let's dive quickly into it. Just to keep it crisp and simple, I have tried to divide the video into three parts: theory, practice and analysis. In part 1 of this series, we'll try to get a theoretical approach to simple linear regression and its stepwise application to data. We'll learn how everything is dealt in simple linear regression, what are the things that we need, what are the things that we need to make sure we have, and many such other important discussions are coming up. In the second part of the video, we'll do the fun part. We'll have the practical implementation of this model in Microsoft Excel. We'll simply import our data set, put regression analysis into it, and we'll learn how we can simply apply linear regression in very quick and easy steps that we need to follow. In part 3, we'll do the more intelligent and strategically sound part of this tutorial. We'll evaluate the accuracy of our model, which is very important in real life scenarios, as you might get tens of different models, but you need to choose the best models, and how you choose the best model is what we are going to discuss in the third part of the video, and that is the accuracy of our model. Let me also tell you that I expect you to be well acquainted with these topics as mentioned: basic algebra, basic statistics, ordinary least squares method, which as a part of this video we've already created, so do check it out if you've not, and go through that video and learn what ordinary least squares method is so that you can better understand linear regression. And lastly, we need simple common sense and little patience. Well, we call it simple common sense, but it's not so common, is it? Anyway, back on track. We have two simply defined objectives of this tutorial. In the first objective that we have is to find evidence if there exists of a statistically significant relationship between two quantitative variables. Oh, that's a big sentence. Let's understand it well. We need to find an evidence. We need to observe if there exists a relationship between two variables that we are trying to fit into our model. Now this relationship should be significant, and significant not in common terms, in statistical terms. Statistical significance means that there must exist a very defined relationship between those two variables. There obviously are going to be chances for some errors, but those errors should be minimal. So coming back to the topic, once we find the evidence, we will often observe that this evidence is of three types. It can be positive, negative, or no relationship at all. Now positive and negative is easy. Linear positive relationship, a straight line with slope greater than 0, and a negative linear relationship, a line with negative slope. And then comes the no relationship case. Now this is the crucial case which you need to always keep in mind. In real life scenarios, we are often going to get data sets in which when we try to observe the relationship, we will sometimes see that it's positive and sometimes feel that there exists no relationship. So we need to always keep in mind how to judge that well, and that's where the common sense comes into play. Now once you've tried to set the relationship, you must always find the significance or the level of significance in that relationship, which you can always calculate by mathematics. Now the second objective of this tutorial is to find if there does exist a linear relationship between those two, a statistically significant relationship between the variables. We need to now use that relationship to apply it for our benefit. What is our benefit? We can try to predict or forecast unobserved values, or values which we could not calculate or observe in reality, which we can simply observe by using our past data sets, trying to create model which will help us to predict and forecast future values or values that we are unaware of by simply using the values that we already possess. Now it's going to be very complex and also very simple. You'll see and you'll love it. Now one step to always learn something is by asking a lot of questions. It is one of the greatest ways to get something deeply embedded into your brain. And as they say, curiosity drives knowledge and knowledge drives success. So always be curious. Now, the first part of curiosity is what? What is it that we are trying to learn? What is linear regression? Now, linear regression is basically a mathematical model that approaches to explore the relationship between two variables. Now, when I say mathematical model, it basically means that it is an equation, a mathematical equation which will give you all the stories about your data, which will tell you how one thing is dependent on another and how one changes when the other changes. The linear regression model consists of two variables. Now they can have many names, but what they signify is that independence and dependence. Now, independent variable is also called feature variable or explanatory variable, which are used to predict values from past values. Now, this is the variable which we are going to use to predict the values. And whose value are we going to predict? We are going to predict the values of the dependent variable. The dependent variable, also known as the predictor or response variable, whose values which we are trying to predict based on the dependent variables. Now, in linear regression, talking strictly about linear regression, there are two cases. One is the simple linear regression, where there is only one independent variable, and the other case is called the multiple linear regression, or as we understand from the name, it has two or more independent variables, multiple independent variables. Now let me tell you, and let me get this through with you. In any linear regression model, or in any regression analysis, or in any analysis model, in fact, which we are going to read about in the coming videos, we always have just one dependent variable, or just one variable whose values we are trying to predict. And there can be one or many independent variables, the variables whose help we take to predict the value of our one single dependent variable. Moving on. Why do we study linear regression? Why is it that important? It is important because it makes forecasting and calculations very, very easy. For example, if you go to a mine in any part of the world, you are going to see that there existed a very big problem of trying to estimate the amount of pressure applied on the rocks. As you can simply imagine by your common sense, as I said, it is very crucial to try and understand and evaluate the amount of pressure required to break some huge rocks inside the mines. If you apply less pressure, the rock is not going to break, but if you apply a large pressure on it, there is the chance of spoiling the whole mine, getting into trouble simply. So to try to estimate the pressure of breaking huge rocks, we can use linear regression. We can try to break 10 huge rocks of different sizes, and we can try to collect the data, the amount of the the weight of the huge rock that we are trying to break. Then comes the pressure that we've calculated to break the huge rocks, and just by simply getting 10 data points of these two variables, we can try to estimate the pressure required to break rocks of different sizes by using linear regression. It's that easy. Now, to apply linear regression, we must always follow 4 simple basic steps. The first step is one of the most important steps that you should always keep in mind. It is the first step. That is why it's basically a safety check that if you're trying to evaluate something with linear regression, is it worth the effort? So what do? You plot your data that is available to you. Now in simple linear regression, we just have two variables, so it is very easy to plot in y and x, and you can observe or check for evidence of linearity. Yes, as the name suggests, it is linear regression. So the most important requirement of this model is linearity. Your data set must be linear, and we'll understand in the further coming slides about what is linearity. But let's come back to step 2. Now step 2 is where we actually create the model, is where we actually use our data set that is available to us, and we use that data set to calculate the parameters of the model. As I said, the model is basically a mathematical equation. So the parameters of the model is basically the unknown variables of your mathematical equation. Once you get to know about those unknown variables, you have created your model, and you can finally use it in step 3 to predict, to start making your predictions. It's very, very simple. And the last and the fourth step is basically an advanced version of learning simple linear regression. It is how we calculate the accuracy of the model and how you apply changes in the model to get better accuracy from your model. So accuracy of the model, presently it's not so important for you as you are simply learning the fundamentals of linear regression, but once you become a data scientist, a data analyst in a big top firms, you are going to need better accuracy in every model that you create. So what happens then is that you must try to improve your model, improve the accuracy of your model time and again, and for that you need to consider various parameters which we are going to discuss in part 3 of this video, so don't miss it. So finally, step 1, here we go. First of all, as we already know, we need to do a safety check. We need to observe that our data set or our data points as plotted on the x and y axis are linear or not. As you can see here, the lines A, B are perfectly linear, one having B having a positive slope and A having a negative slope. Now C is also linear. It's basically a straight line with zero slope. It is a constant value. So we will not keep these values as well. Just to make sure, we'll only get attracted to values or data sets which have these two relationships between them. D and E are basically nonlinear relationships, and if we acquire data sets of these values, we must not apply simple linear regression models. We have various other models to estimate values when our data sets have nonlinear relationships. So first, plotting our data on the x and y axis on a scatter plot, we assume and we see that there is a very nice deal of linearity between our data sets, and thus we can proceed as our step 1 is cleared. Now moving further, now we have the legendary simple linear regression model. It is basically a mathematical equation which is y equals beta naught plus beta 1 x plus epsilon. Epsilon here is the random error term, the errors in each observations which arrive due to the noise in miscalculations or various other factors. Now epsilon is something which is a little advanced topic for simple linear regression, so we'll kind of avoid this right now. We'll understand what the most important part of this model is. This right here, beta 1, is one of the most important parts of this model. It is the coefficient of independent variable x. It tells us that in a unit change of x, what is the effect or what is the factor by which y is affected. And beta naught here is our intercept parameter. It is basically a constant value. It tells us where our model or our mathematical equation intersects with the y-axis. Y, as we already know, is our dependent variable and x is our independent variable. So we are ready to move forward. Now the estimator equation or our predictive model is basically, as you can see here, the actual line equation of our model. It is the expected value of y when we already know the value of x. So the value of x is already known to us, which we simply put in this right hand side of the equation, and we get the expected value of y or the prediction which we want to actually know. Beta naught, our intercept parameters, is what we need to calculate, and beta 1 is another parameter of this equation which we need to calculate. Just a small note right here, there is no error term in the estimator equation, as in a linear equation we assume that our error variable is normally distributed, and from basic statistics we know that normal distributions have zero mean or zero expected value. So moving further, well, it was a long tedious explanation and there was lots of theory, so I expect you didn't sleep by now. Don't worry, we'll just get it done with in 2 to 3 minutes. So till then, just hold on and have patience. Moving on. Now, how is it done? Our aim is to fit the line in the data set which has the smallest sum of squares of residuals. Now the term smallest sum of squares of residuals is basically from the OLS algorithm, the video of which you must have seen by now, and here we basically use the OLS algorithm to calculate the parameters. So definitely go and check out the OLS algorithm if you have not done it so. And once we've done this, once we fit the line on the data set, we use this model, this line, this mathematical equation to predict new values of y based on the equation we already have for a new value of x. So Now I can simply give you the slope parameter formula, which is beta 1 equals summation of product of xi minus xm and yi minus ym upon the summation of xi minus xm whole squared. Now I is basically the ith observations, so if you have n observations, I would range from 1 to n, and basically this summation is for over I equals 1 to I equals n, where you simply add the observations, the calculation of xi minus xm whole squared to sum over the entire range of values available to you. Xm and ym are basically the mean values of x and y data sets, where mean values, as you know from basic statistics, is the sum of the values of x divided by the total number of observations of x, and same as for y. Now intercept parameter is very easy once we've calculated the slope parameter, because now as we know the basic equation of the line, we can simply put b1, which we've already calculated, and in place of y and x we simply replace them by ym and xm, as they are the expected values of x and y. And once we put these three in the equation, we get the value of b naught, and visualization of beta naught or b naught, as you can see here, is the point where which the model or our line intersects the y-axis. Now this beta naught value can be positive, if can be positive or negative. Like here you can see it's positive, as it is intersecting the y-axis above the origin. Well, it might change also, as the slope of this line can be different, and this line might be crossing this origin and might be intersecting the y-axis somewhere over here, and can be negative also, and it can also be zero if it passes through the origin, which is very obvious. Now moving on, let me give you the final tiny glimpse of the whole process. First step, where you observe linearity, we've got the linear plot, and we are like clearing the stage 1. Then we calculate the various parameters, beta 1 parameter, beta 0 parameter, and we finally get our line equation, and then we plot this line on our data set, and we simply, you can see there are some data points below this line, some data points above this line. These are basically the error values, the difference between the predicted values and the actual values, and here you have your simple linear regression model or the mathematical line. Now you can simply put different values of x and project them upwards parallel to the y-axis, and the point of intersection of this line, again project this line parallel to the y-axis, and you can get your predictions easily. So finally, that's all there is for theoretical understanding of regression. Time for some real life practical data analysis in Microsoft Excel. So see you in part 2 of this tutorial. Thank you.